This video is going to look at notes comparing exponential and logarithmic forms and also taking the inverses of exponential and logarithmic functions. First, we're going to look at the different forms we can write our equations. Exponential equations can be written in two forms, exponential form and logarithmic form. With exponential form, we have a base. That base is raised to an exponent, and we're going to call what you get when you evaluate that the answer. If I wanted to switch this over into logarithmic form, I would now have a log expression. The base of my logarithm is the same base as the base of my exponential was. What's inside the logarithm is the answer, which is what used to be by itself. And what used to be in the exponent is now by itself on the other side from the logarithm. So this is how we'll switch between exponential form and logarithmic form. If I want to write 2 to the third equals 8 in logarithmic form, I'm going to have a log expression. The base of my logarithm is going to be 2 because 2 was the base of my exponential. The 3 used to be with the 2, so the 3 is now on the other side by itself. The 8 used to be by itself, so the 8 is now inside of the logarithm. This expression would be read, the log base 2 of 8 is equal to 3. Remember, the log base 2 of 8 means 2 to what power gives me 8, and the answer is 3. The result of evaluating a logarithm gives you the exponent. Pause the video while you try to write y equals a to the x in logarithmic form. The base of the exponential was a, so the base of the logarithm is a. The y used to be by itself, so the y is now inside the logarithm. The x, which used to be with the base, is now by itself on the other side of the logarithm. So the base stays the base, and the other two switch partners. If the x used to be with the base, it's now by itself. If the y used to be by itself, it's now with the base. To convert from logarithmic form into exponential form, we're going to use the same idea. In the log base 7 of x, 7 is the base, so 7 will be written large, and that is the base of our exponential. The exponent in this problem is going to be the number that used to be by itself, so 5 is now with the base written as the exponent. The number that used to be inside the logarithm, which was the x, is now on the other side away from the 7 by itself. So I have 7 to the 5th is equal to x. Pause the video while you try to write y equals the log of x in exponential form. For this, we have to realize that we're missing the base. The base is 10 for this problem, and that's written down here. The log base 10 is such a frequently used base that we call it the common logarithm, and we often leave off the little 10. That's also what the log button is on your calculator because it just says log and there's no base written. Pause the video while you try this one. The base of the logarithm was 10, so the base of the exponential is 10. The x used to be with the base, so the x is now by itself. The y used to be by itself, so the y is now the exponent. The base stays the base, the other two switch sides. Now we're going to look at finding inverses with exponentials and logs. For any function, to find an inverse, you switch x and y and solve for the new y. The other thing we could do is make the backwards flow chart and work through it that way. In example number 1, we're trying to find f inverse for this function. So in my original problem, I'm going to think of this as y equals the log base 4 of x. When I find the inverse, I switch x and y, and this becomes x equals the log base 4 of y. Now we need to get the y by itself. To get the y by itself, we're going to convert from logarithmic to exponential form. The base of the logarithm is 4, so the base of the exponential is 4. The y used to be with the 4, so the y is now on the other side. The x used to be by itself, so the x is now in the exponent. So here's my function. I can write it with inverse function notation. F inverse of x is 4 to the x. It should make sense, since logs and exponentials were inverses of one another, that a log base 4 function will have an inverse of a 4 to the x function. That would also make us think logically about the opposites happening. In number 2, we're trying to find the inverse of f of x equals 6 to the x. If I wanted to write this in y equals, I would have y equals 6 to the x. When I go to find the inverse, I switch x and y. So now I have x equals 6 to the y. In order to get the y by itself, I need to convert to logarithmic form this time. So I'll have the log, the base of the log will be 6 because that was the base of the exponential. The y that used to be in the exponent is now going to be on the other side away from the 6. And the x that used to be on the other side is now inside the logarithm. If I wanted to write this in inverse function notation, I put the little -1 in the exponent, and I have f inverse of x is the log base 6 of x. The opposite of taking 6 to a power is doing a logarithm base 6. If I wanted to write this in y equals form, I'd have y equals the log base 3 of x plus 2 minus 5. I should realize right now that in my inverse function, the base of my inverse function is going to be a 3. So the inverse of a log base 3 function is a 3 to the x function. The opposite of add 2 on the inside is subtract 2 on the outside. The opposite of subtract 5 on the outside is add 5 on the inside. So this is my inverse function. If I wanted to go through those steps algebraically, I could take my original function, I could switch x and y, just like I did on the previous example. The only difference is, in this one, before I can convert to logarithmic form, I have to move the 5 over to the left side of the equation because my formula only allows me to have a base, something inside the logarithm, and an answer. So this x plus 5 over here has to be put together as one thing. So the base stays the base, so this 3 stays the 3 in my answer. What used to be inside the logarithm would then move over and be by itself. I rewrote that there. So the y plus 2 is now over on the other side by itself, and the x plus 5 that used to be by itself is now in the exponent. The only problem with this is my y isn't by itself yet, so I need to subtract 2 from both sides to get that y by itself, and that's how my 2 wound up on the outside. You can do it either way, just think about logically, or go through the steps algebraically. Going through the same type of example in number 4, our original function was y equals 2 times 3 to the x minus 4. If I'm just going to work my way through this logically, my inverse function, the opposite of a 3 to the x function, my parent function is going to be a log base 3 of x function. The opposite of subtract 4 inside is going to be add 4 outside, and the opposite of times 2 outside is going to be divide by 2 inside. If it's inside, I need to put that inside the logarithm there. So this is my inverse function. F inverse is the log base 3 of x divided by 2 plus 4. If I were to walk through this algebraically instead, I would switch my x and y, and I'd have x equals 2 times 3 to the y minus 4. I'm not allowed to have anything times my exponent when I switch it over to logarithmic form, so I would divide both sides by 2. So now I have x over 2 on the left. I have 3 as my base on the right. and y minus 4 is my exponent. So when I go to convert forms over to logarithmic form, the base of my exponent is the base of my logarithm. What used to be by itself is now inside the logarithm, and what used to be in the exponent would now be by itself. That would make a y minus 4 on the left, so then I move it over and switch it to a plus 4 when I move it on the right, and that's the algebraic method. The last piece of today's lesson is evaluating logs on a calculator. As I mentioned earlier, the log button on your calculator, which is right here, this log button, that log button is a log base 10. The only log that our calculator can evaluate is a log base 10. If we want to do a different base, we need to use the change of base formula. The change of base formula says the log base b of x is equal to the log of x over the log of b. In other words, you're going to do the log of what you're taking the log of, and then we're going to divide that by the log of the base. If we want to find the log of 10 on our calculator, we just need to take the log, regular log button. Let me get this stuff off of here. And then I'm going to type the 10. I have the log of 10, which is 1. That should make sense that the log of 10 is 1, because what does the log mean? That means the log base 10. So 10 to what power gives me 10? 10 to the first power gives me 10. If I wanted to find the log base 2 of 8 on my calculator, I need to type into my calculator the log of 8 divided by the log of 2. I don't have to use the parentheses when I'm typing this one if I don't want to, because there's only one thing inside my logarithm. If you have a TI calculator, the parentheses automatically pop up, so it's important you close them. So this is equal to 3. That should make sense because log base 2 of 8 means 2 to what power gives me 8, and the answer to that is 3. Not all logs will be that obvious that you can figure them out in your head, especially if they're irrational numbers or numbers that we cannot express without this logarithm expression. To type the log base 3 of 5 in my calculator, I need to type the log of 5, that's the log of what I'm taking the log of, divided by the log of 3, which was the log of the base, and that gives me a decimal answer of 1.4649. 1.4649. I like to give 4 places after the decimal, and I just chop it off. I call that truncating, chopping off, because I want to be sure I realize this keeps going forever and ever. I cannot express this any other way than writing it in logarithm. The base of the logarithm was 3, and what I'm really asking right here is 3 to what power gives me 5? There's no nice expression I can put in this exponent so that 3 to that power gives me 5. I know 3 to the first power is 3, and 3 to the second power is 9, so this thing in my exponent better be somewhere between 1 and 2, and it is 1.4649. To put a log in a graph, I just need to go into my y equals, and then I'm going to graph what I want. If I want the log base 2 of x, I'm going to have the log of x divided by the log of 2. I can then put this in a standard view window and graph it, and there's my logarithmic function. Be sure if you're trying to graph things with logarithms in your calculator that you realize if you were to graph something like the log base 2 of x plus 3 and then a plus 5 on the outside, what we would need to write in RY1 is the log, we need a parenthesis, x plus 3. Now the 5 wasn't with the base, so the log of x plus 3 gets divided by the log of 2, and then the plus 5 gets written out on the end. So if I'm putting this one in my calculator here, I have the log of x plus 3 divided by the log of 2, which was the log of the base, and then the plus 5 was out there on the end, and I can draw it. Be sure you realize when your calculator draws this, it's not going to show you have an asymptote right here at x equals -3. And it's not going to show you that this thing keeps going down forever. When you put it on your graph paper, you need to show both of those things, arrows on both ends, your graph keeps going down, and it's got an asymptote at x equals -3 because we scooched this graph 3 units to the left with the plus 3 on the inside.